Hi guys, this video is meant to cover Unit 18 Artificial Intelligence of the Cambridge 9618 A2 level Computer Science syllabus. As part of this unit, you will study about graphs and a bit of graph theory. You will study about machine learning, deep learning, and reinforcement learning. You will also study about supervised and unsupervised learning and what their applications are, followed by things like backpropagation, gradient descent, and regression, which are terms associated with machine learning models. We will begin with the very first section, that is, show understanding of how graphs can be used to aid artificial intelligence. Once again, the very first section we'll be looking at is how graphs can be used to aid artificial intelligence. Now, the graph that we discuss about in AI isn't the same graph that you might be familiar with in mathematics or any other subject. A graph in computer science is a data structure. It's a data structure that consists of nodes, which are known as vertices, and edges, that are also known as connections. And these nodes have edges in between them, connecting the nodes together. And this is what forms the graph. So a graph is a data structure consisting of nodes or vertices connected by edges or connections. Let me draw a graph and show you how it looks in a sort of representative format, right? I'll try and show you how these nodes and edges connect to one another so that you can visualize how a graph looks. A graph is made up of nodes, where each node can be represented using a circle. Usually, each node is given some unique identifier, like a letter. For example, this node here may be given the letter A. The node here might be B, the node here might be C, and the node here might be D. Once the nodes have been given unique identifiers, the nodes can be connected together using lines. These lines are best kept straight, and these lines are what we refer to as edges. Some nodes are connected to other nodes, whereas some nodes are connected to every other node. For example, node A is connected to C, D, and B, whereas node B is only connected to A and D. So you can expect that some nodes may not connect to other nodes. In addition, these edges may sometimes have a number written on top of them. Let me write number 5 on top of this edge from A to B. This number is referred to as a weight, which signifies some metric of the graph. Now, graphs are used for a variety of computer science problems, so the weight's purpose might depend on the problem itself. But for example, if you imagine that the nodes represent cities or towns, and the edges represent the roads connecting these towns, the weight could potentially be the distance of the road, or maybe even the amount of traffic on the road, or maybe even the amount of time it takes to travel on that road. So the weight is a metric or a cost, you could imagine, that's allocated to each edge of the weight, each edge of the graph. Now, having said that, let me complete the labels of the graph right here, guys. We have nodes, weights, and you also have your edges. Now, there are different types of graphs depending on the characteristics of these nodes and edges and weights. Let's take a look at these different types. We first have undirected versus directed graphs. Undirected graphs are graphs whose edges have no direction and are often relevant in road maps. Directed graphs, also known as digraphs, are edges with direction. So for example, if every edge on this graph has an arrow signifying what direction each edge points to, this would become a directed graph or a digraph. But usually in the Cambridge A2 level computer science syllabus, you encounter undirected graphs only. Then let's take a look at weighted and unweighted graphs. Just like how undirected and directed are controlled by whether the edges have a direction, weighted and unweighted is controlled by whether the edges carry a cost or distance. That is, whether every single weight has a number. Every single edge, beg your pardon, has a number on top of it. Now here, only one edge has a number, but imagine you allocate numbers to every single edge on this graph, then this graph would become a weighted graph. But if there's a graph where the edges are not numbered, where all edges are treated equally, then this would become an unweighted graph. Weighted graphs are especially important and especially relevant when you try to represent map distances and energy graphs. Finally, we have cyclic versus acyclic graphs. Cyclic graphs are graphs where loops can be achieved. Loops are full round paths across the graph, where you can start at a node, travel along a certain set of paths, and come back to the same node, right? Or a certain set of edges and come back to the same node. The edges that are covered across this journey is referred to as a path. And if this path ends up back in the same place without reusing the same edge twice, this could be referred to as a cycle, right? So if a graph has cycles where you can establish paths that loop back to the initial node, you can refer to those graphs as cyclic graphs. But if there are graphs with no loops, especially relevant to these things like decision trees and dependency graphs, these graphs are referred to as acyclic graphs. Now, the reason I introduce these terms to you is not because you'll get these terms at the exam, but because you need to know what kind of graph you'll get at the exam. And now that you know undirected versus directed, weighted versus unweighted, and cyclic versus uncyclic, cyclic versus acyclic, sorry, I can now tell you that in the exam, you'll most often get undirected graphs. You'll most often get undirected graphs that are weighted and may often be cyclic, right? The word cyclic isn't that important because sometimes graphs may be acyclic as well. But most often in the exam, the graphs you get, and where you get graphs in the exam are pertaining to shortest path finding algorithms, right? We'll be looking at two algorithms called Dijkstra's algorithm and A-star algorithm as part of this section. Under those sections, you will get graphs at the exam, and those graphs are most often undirected, weighted. And of course, you can also find cycles through those graphs. But having understood what undirected and weighted means helps us understand the kind of graph we'll get at the exam. All right. Hopefully this makes sense to you guys. Next, let's take a look at a few use cases of graphs. Graphs are used in pathfinding and navigation, where it's used in games, robotics, and GPS systems. And it's used, like I said, in algorithms like A-star and Dijkstra to traverse graphs to find optimal paths. So if you want to find the shortest path from a node to another, you can use algorithms like A-star algorithm and Dijkstra's algorithm. Graphs are also used for knowledge representation, where graphs are used in semantic networks or knowledge graphs to link concepts or entities together. And graphs are used in AI assistance for information retrieval purposes. Graphs are also used in problem solving and state space, where each node could represent a possible state, where the edges could represent possible transitions between those states. If you guys remember your AS level content from programming, you might remember learning about something called a state transition diagram. A state transition diagram can also be represented as a graph, where state transition diagrams are helpful in planning related problems and puzzles. Finally, graphs are important in social networks, where users may represent nodes in the graph, and friendships between those users may be represented by edges. And these graphs may be used in recommendation systems to recommend mutual friends, or recommend content for the user to consume. Now, an application that's very specific of graphs to the syllabus is neural networks, where neural networks can also be built using graphs, where neural networks have these things called neurons, which can be built using nodes. And they also have weights, which are costs or numbers assigned to each connection in the neural network to signify how important that input is. And those could be represented using the edges. Now, of course, we'll be looking at this in more detail, but neural networks is also a very specific example that we have in our syllabus to discuss about an application of graphs. All right, that thereby concludes, ladies and gentlemen, the first part of this topic, show understanding of how graphs can be used to aid AI. All right, having understood graphs and all their characteristics and their users, we are now ready to look at the first path-finding algorithm in the syllabus. Now, in our syllabus, you need to know how to find the shortest path from one point in the graph to another. And you can achieve this using Dijkstra's algorithm as well as A-star algorithm. You need to know how to work them out at the exam. And if you take a look at past paper questions from, of course, past papers, you might encounter questions pertaining to Dijkstra and A-star, where you have to work out the shortest path and the relevant calculations, right? So I want to walk you through how those calculations are done. So that way you are prepared for the exam if you get a question on Dijkstra and A-star. Right. Dijkstra is the name of the person that created this algorithm, and I encourage you to search him up. But Dijkstra's algorithm is what we refer to as a greedy algorithm. To find the shortest path from a source node in the graph, that means a starting node in the graph, to all other nodes in the graph. Keep in mind, Dijkstra has no destination. Dijkstra finds the shortest path from any starting node to every other node. And this is in a weighted graph, where the graph must have on its edges a number. And each of these weights must be non-negative. Now, I hope these points are clear, but what does it mean for Dijkstra to be greedy? It means that it attempts to do a bit of a brute force approach when it comes to finding the shortest path, because it discovers or traverses along every possible path in the graph before it realizes what the shortest path is. Now, the algorithm for Dijkstra is given here in yellow color, but I won't be going through this algorithm directly because I want to show you a practical example of it and then apply the steps of the algorithm one by one. Let's begin. Here, we have a nice graph which has 5 nodes, isn't it? This graph has 5 nodes labeled A, B, C, D, E, and the nodes have connections between them, where each connection has a weight allocated to it. But can you spot a single edge or single connection that is missing a weight, guys? I'll give you guys 3 seconds. 3, 2, 1. There is one weight that is missing, or one connection that doesn't have a weight. And that's, ladies and gentlemen, this path from A to D, or this connection or edge from A to D. And let me give it a weight, for example, like 5. Okay, so now everything in every edge in this graph has a weight, which makes this a fully weighted graph, and no edges have directions. As a result, this is an undirected weighted graph. Undirected weighted graph. All right. Perfect. Now let's understand how Dijkstra's algorithm helps us find the shortest path from the source node, which has a nice label called source, which is node A, to every other node in the graph. Please ignore these final cost, working cost labels and the discovered path label. I'll explain them to you as we go on with the algorithm. Right. Now, keep in mind, we are starting at the source and our goal is to find the shortest path to every other node. Now, the very first step in this Dijkstra algorithm is to basically assign the source node with this so-called final cost of 0 and assign every other node with a working cost of infinity. Now, what on earth does that mean? The final cost, ladies and gentlemen, is the shortest path cost from the source to that node. Shortest path cost from source to that node. Right? And the working cost is sort of the path cost that we've currently found to be the shortest, but maybe shorter later on. So it's basically just the shortest path cost that we found right now. So you can imagine that this is like a temporary shortest cost. Actually, you can't call it shortest then, can you? You can just call it temporary cost to reach a node. Temporary cost. And cost is a term that we refer to as the total of all the weights or total of all these numbers to go from a particular node to another. That's what cost means. So for example, if someone asked you what the cost is to travel from C to B, you could say that the cost is 3. So the cost is essentially how long or how much time a path takes to travel. Again, this number is an arbitrary number. We don't know what this number represents because we don't know what problem we're trying to solve using this graph. But usually the graph problems that you get at the exam are framed as locations for the nodes and roads as the connections between the nodes. So you can imagine that these numbers represent the length of the pathway between these nodes, right? But again, it's less about the application, but more about its generalization, right? How you can use this to solve any graph problem. But again, we give the source node a final cost of 0 and all the other nodes a working cost of infinity, where every other node gets a temporary cost of infinity and the starting node gets a final cost of 0. Now let's ask ourselves why this is. Now the final cost is the shortest path cost from source to that node. Now, if you are starting at the source, this 0 represents the cost to go from the source to the source, right? It's the shortest path cost from source to the source again. I mean, that's nothing, right? There is no cost to travel to the source if you're already at the source. This makes the final cost of the source node 0. But how come we assign infinity to all the other nodes as their working cost? Of course, the reason why we assign working cost and not final cost is because we don't know what the shortest path to those nodes are. But the reason why we assign a working cost of infinity is because right now, we haven't gone to any of these nodes. So we are willing to assume that the distance to them is infinite because we haven't discovered a single path to those nodes yet. And we want to assign the largest possible number to these nodes at the beginning as their working cost. So that way, if you even find a slightly smaller number, that number can replace this infinity by itself, right? So we essentially want a number that can be replaced by something smaller. So the best choice for that is a arbitrarily large number like infinity. All right, hopefully that makes sense to you guys. We can go back to the algorithm now, and you can see that the algorithm says step 1, set the final cost of the start node to 0, which is what we did, and set the working cost of all other nodes to infinity. You can see the final costs in green color, and you can see the working costs in pink color or magenta. Right, now it's time to go through Dijkstra's algorithm. Let me go to the algorithm and see what it asks us to do. while there are nodes without a final cost, right? While there are nodes without a final cost, step A, select the node with the lowest working cost that doesn't have a final cost. Set its working cost as the final cost. And for each neighbor of this node, calculate its new cost by adding the final cost of the current node plus the edge weight. And then if the new cost that we calculate for this neighbor is less than the neighbor's current working cost, we update the neighbor's current working cost with this new cost. That seems like a lot, but let me explain this to you step by step. Now we start off at the source. We look at what are the nodes that are neighbors of the source. In other words, what nodes are connected directly to the source. That is B, C, D, and E. What we then do is we calculate the cost to travel to those nodes from the source by adding the source's own final cost with the path cost to that node. So the source's own final cost is 0 because the cost to the source from the source is 0, right? And we add that with the path cost of 6. This makes 0 plus 6 a total of 6 to travel to B from A. So the total path cost to travel to B from A is 0 plus 6, 6. Now you need to ask yourself, is the 6 that we calculated as a path cost for B less than the current working cost for B? I mean, anything is less than infinity, right? So you can imagine that this infinity gets replaced by 6, which is what in the algorithm this means. Update the neighbor's working cost to new cost if the new cost is less than the neighbor's current working cost. So the neighbor B from source has been allocated the working cost of infinity, and the 6 that we calculated now, the new cost is definitely less than infinity, so we can replace the infinity by 6. But we can't say that that's the final cost yet because we may discover a shorter path to B. All right. Okay, now let's proceed. So we've just finished looking at A's B neighbor. Now it's time to take a look at neighbor C. The path cost to neighbor C is 0 plus 2, which will be 2, which can definitely replace infinity because 2 is less than infinity. That's done. And then let's look at A to D. A to D is 0 plus 5, 5, which is less than infinity, which I can then replace infinity by. Then what do I have? After this, I can take a look at A to E. A to E is going to be 0 plus 10. The path cost from A to E is 10, which I can then use to replace the infinity with. And that concludes the discovery of all the neighbors of A. Pretty cool, right? Okay. Now, one thing that I forgot to do was to mark that A has been discovered or A has been given a final cost. And in the exam, we usually do that by putting a nice tick mark to A to signify that A has been fully discovered, right? And one thing we do while we, discover these paths is we write them down in the working area of the exam. So let me just go through this once again. We first discovered the path from A to B, which I can write down under the working or the discovered paths section with a cost of 6. And then we discovered the path from A to C with a cost of 2, with a cost of 2. And we discovered the path from A to D with a cost of 5. And then we discovered the path from A to E with a cost of 10. Declaring these costs as the final working costs for this round of Dijkstra. And, as a result, we have reference to all the paths we have discovered in this final round of traversal, right? So try to make sure that you guys denote your paths as you encounter them. And one more thing you can do to avoid confusion later on in the exam and later on in this process is each path you discover, you can cross it off. So you discover the path from A to B, you discover the path from A to C, you discover the connection path or edge from A to D, and you also discover the connection from A to E. So I've crossed them off to indicate that they are done, which means that I don't mistakenly go through those paths again because I know that those paths have already been discovered. Okay, so what I described to you was essentially these 1, 2, 3, 4, 5 steps, right? I've just discussed these steps. Now, and to repeat them. And now that we've gone through these steps once, we can probably understand these steps better, where I start from the beginning. While there are nodes without a final cost, I mean, we still have a lot of nodes without a final cost, right? The only node that has a final cost is node A. Node C with a final working cost of 2, D with 5, E with 10, and B with 6, all still don't have a final cost. So what do? That means I can repeat. I select the node with the lowest working cost that doesn't have a final cost. So ask yourself, out of the nodes that don't have a final cost, with which node has the lowest cost, lowest working cost to be precise? That has to be C, right? C has a lowest working cost of 2. So then I choose that node as the next point I traverse on, right? So I set its working cost next as the final cost. I set its working cost next as the final cost. In other words, locking it in, and thereby declaring node C as a discovered node. So I can put a nice tick next to node C and make this number 2 green color to indicate that that has now become the final cost. So each time I discover the nodes adjacent to a particular node, I repeat this process on the next node that has the lowest final cost. And keep in mind, when I select the next node that has the lowest final cost, it doesn't have to be the adjacent nodes. It could be some disconnected node that you are yet to discover as well. So adjacency doesn't matter when it comes to selecting the next node. We just select the one with the lowest working cost. And we make that lowest working cost the final cost, and then we proceed. Right, so now we repeat, but now this time for every neighbor of C that hasn't already been discovered. So what are the neighbors of C that haven't already been discovered? Now A is a neighbor of C, but it's already discovered, so I don't worry about that. It already has a final cost, or it already has a tick. I then look at C to B and then C to D, the only two neighbors that haven't already been discovered. What do? I then try to calculate the path cost to B, but keep in mind from A, right? The source is still A. So what do we do to calculate the path cost from A to B via C, given this new path? What we do is we add the current final cost of C to the edge weight from C to B, which makes it 3 plus 2, 5. Now you have to ask yourself, is 5 less than the current working cost that we got for B? 5 is less than 6, yes. So what we can do is we can effectively cut off this 6 and write 5. And we can also represent this new pathway we've discovered on the discovered paths section. And you can write these paths out on the working of your exam, right? So we can write down that I've now discovered a pathway from A to C and then C to B that has a cost lower than what I discovered earlier, which is 5. So you can even cut this off to indicate that that has been replaced with a new cost now. A new shorter value, a smaller cost. Anyway, having said that, we can now cut off this path because it's now discovered as well. And then I can proceed on to the next neighbor of C, where I can check if the total path cost to D is less than the current working cost of D. So the total path cost to D via C is 2 plus 4, 6. Is 6 less than 5? No, not really, is it? 6 is greater than 5. So this path is longer than the direct path from A to D. So we don't replace it. Can directly just cut off this route and we just proceed. So we don't even have to write this down here because we know that this path with a total cost of 6 is definitely larger than whatever we discovered for D. There's no point in really having to, go through this path again. All right. Hopefully that makes sense to you guys. Now, having said that, we can now repeat this problem or repeat this task on the next node that has the lowest working cost. The next node that has the lowest working cost is a choice between B, D, and E. So the choice is between either B with a cost of 5, D with a cost of 5, or E with a cost of 10. So you might imagine that the cost is now essentially equally shared between D and B, right? It's both 5. So the next choice is really arbitrary. It's up to you. You can choose whatever you want. Let me pick A, B, C, D, E, F, G, H, I. Yeah, let me just pick B. You can do eeny, miny, mo if you'd like. Of course, there's a proper data structure governing this, which you will learn if you study these algorithms in the future and if you learn their implementations. But for now, you can just make it an arbitrary choice. So let's just pick B. Let's just pick B, right? Now we have to discover all the nodes that are connected to B that haven't already been discovered. So let me first make sure that B is given a final cost of 5, because that's the shortest cost to B that we've calculated. So that's now final. I can tick it off to also ensure that, that's finalized. And what I can do next is I can look at all the nodes that are adjacent to B that haven't already been discovered. It has to be E, right? A is been discovered already, C is already discovered, P is not connected to D, so I can't do anything about that. So the only node that is yet to be discovered is B to D, right? B to E, sorry. It's E. So let's now repeat this from B to E, guys, where I take the current final cost of 5, add that to the path cost 5, thus making this 5 plus 5, 10. Now, is this less than whatever we calculated here right now for the final cost of E? Not really. I mean, we are saying that this pathway, A to C to B to E, is 10, and it's the same as the direct pathway 10. So in reality, there's no difference in using either pathway, right? So therefore, you could just keep this as it is, because this pathway doesn't reduce the total cost. So therefore, this pathway or this edge is cut off, but the cost isn't updated. But that means that B is also done. And now we have to repeat this on the remaining 2 nodes that are yet to be discovered or yet to be explored. So the next 2 nodes I can repeat this is on D and E. So the only thing that I have to do now is pick the one with the smallest working cost, which in this case is D. I pick D, and then I look at the connection from D to E, because all the other nodes have already been discovered. And keep in mind, I can also make sure that D's 5 becomes the final cost, because that's the current smallest working cost, right? So I repeat this, and I discover the path from D to E now, but adding this 5 to 3. 5 plus 3 is 5, 6, 7. Oh, we just found a path to E that is shorter than whatever it currently had, the 10. So what we can do is we can replace this 10 with a beautiful 8, 5, 6, 7, 8. And I can record this down here to indicate that I found a shorter path to E, which is A to D, and then D to E, with a total cost of 8, right? So that's done, which replaces the previous total cost that we calculated to E, which is 10. And then that means this path has also been discovered, and we're done. And you can see how there are crosses across all the connections or all the edges, which indicates that this algorithm has been completed, or we've discovered all the paths. But we can officially only complete this once we ensure that there are no more nodes connected to E, or there are no more connections of E to explore, which in this case is true, right? There are no more connections of E to explore. So we can declare this also as done, nicely color over this 8 to indicate that it's final cost. And there we go. Ladies and gentlemen, we have found the shortest cost to every single node in this graph, starting with the source. Pretty interesting, isn't it? So look at the benefit of recording all these discovered paths, guys. The benefit of doing this is that at the end, you have 4 distinct annotations on your working that tells you what the shortest paths are and what their shortest costs are. A to C is 2, A to D is 5, A to C to B is 5, and A to D to E is 8. Cutting off these 2 other possible options have also helped me clear some of the clutter, because I know that these are now replaced by routes that are shorter. And at the exam, you may have to write down what the shortest paths are, and you may have to also write down what their total path cost is. But here you can see them very clearly. The final shortest path cost from A to C is the direct path, which is 2. A to D is the direct path of 5. A to C to B is the direct path, beg your pardon, the indirect path to B, that is A to C and then to B. And then the A to E is shorter if you go via D. A to D to E is the shortest path. This concludes Dijkstra. Try to go through this algorithm once again if you want to look at the specifics, but it is essentially the exact same thing I explained here when I did it on this diagram. So hopefully this makes sense to you guys. If you have any questions as usual, please let me know. Right. We can now take a look at A star's algorithm. Right now, A star is essentially an improvement to Dijkstra's algorithm to do what? It's an improvement to Dijkstra's algorithm, right? Which makes it a less greedy algorithm. But it's there to find the shortest path from a source to a target. Shortest path from a source to a target. And this is done by using both a path cost and an estimate to the goal known as a heuristic. A heuristic is essentially a measurement of how close each node is to the destination. And what you realize as one core difference between A star and Dijkstra is that A star not only has a source, but it also has to have a destination. So A star requires both a source as well as a destination node. So Dijkstra finds the shortest path from the source to every other node, whereas A star only finds the shortest path from a source to a particular destination, which means that it may not end up discovering all the paths. It may not travel through all the paths, which is good, right? It reduces the amount of computation we have to do. Now, here is the algorithm for A star, but I'm not going to ever touch this right now because it might seem very complicated to you guys. But I'm going to keep it here for reference later on. But I'm just going to jump into A star with a question, right? And this is actually a past paper question from a previous A2 level 9618 past paper where we were supposed to perform A star on this graph, right? Our goal is to perform A star algorithm on this graph to go from home, which was our source node, to school, which was our destination. Now, without batting an eye to the algorithm, I want you guys to imagine that this is exactly the same as Dijkstra, which means that you would start off by assigning every node except the source a working cost of infinity. Let me do that. Infinity, infinity, and I keep on doing this for every other node except the source. And then I assign the source a final cost of 0. So you can see at the beginning, it's literally the same as Dijkstra, right? I can go back up to the so-called A-star algorithm now, the algorithm itself. And here we have to say we add the start node to an open list, which is just a list that we use to keep track of all our nodes. But you don't have to do this because this is more of like a programmatic algorithm. But don't worry about this, right? All you need to remember is that if you keep track of your nodes the way I'm going to explain it to you, that should be enough. No need to worry about an open list, but I'm just keeping it here for reference because this is how you might implement this if you're doing this using a programming language. But the idea is that you start off by setting the cost of the starting node as 0, and you assign the final cost of the start as the heuristic of the start. That's a very interesting thing. We haven't really looked at what heuristic means, isn't it? Now, the heuristic we realized is essentially an estimate to the goal, right? The estimate to the goal. Now, what does this mean? Estimate to the goal. This is basically how far away you are from the destination node, right? How far away you are from the destination node. So the heuristic is how far is a node from the destination, right? That's what heuristic means. Now, having said this, let's look at our graph. In our graph, the one that's given to us in the exam, there is numbers on top of each node now. Right, I'm going to circle them. These numbers represent the heuristic value, or just the heuristic. What does this mean? These numbers represent how far away you are from the school. So right now, it seems that F is 3 units away from school, E is 3 units away from school, D is 6 units away from school, C is 9 units away, B is 7, home is 14, and A is 10. Now, the reason why we have these heuristics values is because unlike Dijkstra, we want to make sure that every step we take in this algorithm is a step that helps us lower our overall cost. And what I mean by overall cost is that in A star, the way we calculate the cost of traveling to a node is not just by adding the sum of its paths from the source to the destination or from the source to the current node, right? It's that plus something called a heuristic value, which is exactly the values that you see on top of these nodes. So what does that mean? We tend to simplify the equation of calculating the final cost of a node as F equals G plus H. What does this mean? F refers to the final cost of a node. The final cost of a node is equal to G, which is the path cost to that node, plus edge, the heuristic. So unlike earlier, where the only thing that mattered to us in Dijkstra was just the path cost, here it's that plus the heuristic. Hopefully that makes sense to you guys. Now, that's why up here in the algorithm, there's this statement called G start equals 0 and F start equals edge start. What does this mean? G start equals 0 means set the starting node's G value, which is the path cost, as 0. Set start's path cost as 0. And F start equals H start means set the final cost of start to the heuristic value of the start. Now, this is best understood with a nice table. Now, imagine I draw a table where I have my so-called node, the current G value or path cost, and then the edge value, which is the heuristic, and then the F value, which is the total cost or final cost you could imagine. Now, at the beginning, we are at the home. So I can write down under the node section, I begin at the home node. Now ask yourself, when I'm at the home node, what is the path cost to the home? That is effectively the 0 that we began with, right? That's the final cost of the home. The path cost to the home, if you're starting at the node, home itself is 0. The path cost to the home is 0. But the heuristic is what? That's 14. You're 14 units away from the school, which is currently the furthest away you could be from the school, right? That's the heuristic of the school, of the home, sorry. So the final cost of home is going to be not just 0, but it's 0 plus 14, 14. Keep that in mind, guys. Although we write 0 here, this is the G value that we write, the G value. We write our F value here to indicate what the final cost is, which is including the heuristic. But keep doing this where you write the final cost as just G value, because this is what you use to find out the cost to the other nodes, right? So you don't add the heuristic each time when you calculate this of the other nodes as well. All you add is just the path cost, but the heuristic, including the path cost is what we write down in the table here. Okay, hopefully that makes sense to you. Now let's repeat, right? Again, don't stress. This will make more sense when we do a few more traversals, right? Now at the home, we are now going to look at the nodes adjacent to the home, right? Just like Dijkstra. You look at the nodes adjacent to the home. That's A, B, and C. What do we do? Let's just start off with A. Ask yourself, what's the path cost to A? That's the home's final cost, 0, plus the edge or connection cost, that's 1. 0 plus 1 is what? That's a total of 1. So therefore, you can write down from home to A, the G value is 1, because that's 0 plus 1. But what's the heuristic of A? That's 10. That's how far away you are from the school. So then the total is going to be 11. Okay, that's done. And then we look at B. The cost to B from the home is going to be 5 plus the home's original final cost. This is just the path cost, right? 0 plus 5, that's 5. So the cost to B is going to be 5. But the heuristic of B is 7. So I write down 7 here. And what's the total? That's going to be 7, 8, 9, 10, 11, 12. So I realize that the final cost is 12. And something that I forgot to do is with each of these parsers, with each of these traversals, I'm supposed to update the path cost of each of the nodes from infinity to the new path cost. So keep in mind, I set this to infinity, but we just realized that there's a shorter path to A rather than infinity. That's 1. And then home to B, there's a shorter path than infinity. That's 5. Then let's look at the next adjacent node to C, to the home. That's C. So that would have a path cost of 4, which is less than this infinity value. I can write that down here as the path cost from home to C as 4. But what's the heuristic of C, guys? That's 9. So that'll be a total of 9 plus 4, 30. Okay, so I've now finished going through all the adjacent nodes of home. So I can get rid of these temporary markers. And I've also made all the adjustments I need. And I've also discovered all the final costs in the diagram, including the heuristic. So keep in mind, I keep annotating on the diagram the usual working cost, just like Dijkstra, and also the final cost, just like Dijkstra. But down in the table, I note down the final cost, including the heuristic. Now, you may be wondering why we do this. The reason we do this, ladies and gentlemen, is because unlike Dijkstra, what helps us choose which node to traverse next is the one that is, number 1, currently not discovered or visited, and number 2, the one with the smallest final cost. Keep that in mind, please. It's the one with the smallest final cost. So keep in mind, right? I will be going through these steps A, B, C, D, but keep in mind, while the open list is not empty, what does this mean? This is another way of saying, while there are still nodes yet to discover, for each neighbor, I'm going to skip through these steps because they become relevant only later. We calculate the tentative G value, which is the G value from Dijkstra, where we add the current G value plus the weight of the edge. And then if the neighbor is not in the open or closed list, this is just another way of saying whether the neighbor is whether the neighbor has not been discovered or the neighbor has not been visited. If the neighbor has not been visited, or the so-called tentative G value, that is the new cost that we calculate, is less than the current cost of the neighbor, we update the neighbor's current cost, the working cost, you could say. This is updating the working cost. And then we set that neighbor's final cost to the path cost plus the heuristic, right? And then we also record the current node as a neighbor's parent for path reconstruction purposes, but that's more of an algorithmic thing. We don't have to do that when we do it in A star, because we can, when we do it manually, we can of course reconstruct the path from our brains. But when you do it computationally need to make a record of the neighbor's parents so that we can backtrack and find the source. And we also add the neighbor to the open list to indicate that the neighbor has been discovered, but it's not fully visited yet, right? Now, the choice of which node to traverse next is what you see in this step of this algorithm. We select the node with the lowest Fn from the open list. That is a node that hasn't been visited. Now, home is visited, right? Home is visited. So you can imagine that that's part of like the closed list. But A, B, C are part of the open list because they are nodes that we just discovered but haven't been assigned the final cost. So I can tick this off to indicate that this home node has been discovered, but A, B, C are part of the open list. It's still yet to be discovered, right? So what we do here is out of whatever is not yet discovered, now home is discovered, but A, B, C aren't yet discovered. We choose the one with the lowest F value. That choice is between A, B, and C. Which one has the lowest F value? A. So we choose to explore that next. When we choose to explore A next, because it has the lowest A value, we can, of course, set that to be part of the closed list, because now that is effectively the smallest cost. And then we can repeat this on A now, right? We can repeat this on A, where we look at the neighbors of A. What are the neighbors of A, guys? The neighbors of A are B and E. And we repeat this exercise to find the path cost from A to B and A to E. Now, how exactly do we do this? Basically, we add the current cost of A to the path cost AB. That will be 3 plus 1, 4. Right? That will be 3 plus 1, 4. So what we do here is we write down B, path cost is 4. Right? Because this path cost from home to A and then A to B is 4. Now, is that 4 less than the current 5? Yes, so we update that with 4. Keep in mind, if this were larger, we wouldn't be writing this down on the table, right? We won't be writing down on the table. If it's only larger, if it's only smaller, we write it down on the table, right? Okay, so since it's, smaller, we write it down on the table and we update the 5 with 4. And as a result, what we can do next is we can calculate the heuristic as well. And the heuristic would be 7 for B. It'll be 7. I can write that down nicely here. And what else? After this, I can add 4 and 7, which will be 7, 8, 9, 10, 11, making this a total final cost of 11. And then that's done. And then we have to look at E. The total path cost to E would be A's final cost 1 plus the path cost to E, or the edge weight to E, that will be 1 plus 6, which making this a total of 7. Now, 7 is less than whatever E currently has at infinity. So I replace it with 7. And I can write that 7 down here as a part of discovering E. So I can discover that the path cost to E is 7. But what's the heuristic of 7? The heuristic of 7 is 3, which means that 7 plus 3 is going to be 10. All right. Now, that's done. Having discovered all the possible paths of A. And, as Dijkstra, we can also cut off possible pathways that we already discovered if you want to ensure that we don't go through them again, right? But yeah, having said that, we can now repeat, but the next choice is dependent on which node is currently undiscovered. Which node is currently undiscovered? Now, A has been discovered, so I can put a nice tick next to it, right? We've already put a tick here. So the choice of which node to traverse next is between B, C, and E. Keep in mind, B's 12 from earlier is now 11. So we don't consider the 12 earlier. It's now 11 because the path cost from A to B was previously 5, but A to B via, the path cost from home to B previously was 5, but the path cost from home to B via A was a total of 4, which is less than 5. So we take C, B, and E as our decision-making elements next, And who do we choose to explore next? The one with the next lowest final cost that hasn't been explored yet, which definitely has to be E. So we repeat this with E now. Repeat this with E. I can tick that off to indicate that E has already also been fully discovered, you could say, with a final cost of 7. All right, perfect. Right, now we discover the so-called connections of E. The connections of E are E to F and E to school, right? E to F and E to school. Let me write that down. We have the connection from E to F and E to school. So what will this be? The E to F cost will be the path cost that we achieved as the final path cost of E7 plus the edge weight 1. 7 plus 1 is 8, which is going to be less than infinity. So I'll replace it with 8. And then we have this 7 plus the edge weight to school. That will be 7 plus 5. What is 7 plus 5 going to be? That's 7, 8, 9, 10, 11, 12, which will make this infinity a 12. I can record this down in my table as F to school. Sorry, E to F being a total of 8 and E to school being a total of 12, right? E to F being 8 and E to school being 12. And then I can record the heuristics of F and E. What will be the heuristics, guys? My bad, not F and E, the heuristics of F and school. Now, the heuristic of F is 3, right? The heuristic of F is 3, which I can write down here. But what's the heuristic of school? I mean, the school is the destination. So the heuristic of the destination should be 0. Keep that in mind, guys, right? The heuristic of the destination is 0 because we are already at the destination. So the heuristic here will be 0, which gives us the possibility to add 8 plus 3. 8 plus 3 is going to be 8, 9, 10, 11. And then 12 plus 0 is 12. Perfect. So now we've effectively gone through this next layer as well, considering E is now fully discovered. And now it's again to rinse and repeat to figure out which node do we explore next. Now, the choices of which nodes to explore next is roughly between B, which has a final cost of 11, and then F, which has a final cost of 11. Now, the reason we still choose to go through this algorithm again is because even though school has been reached, this might not be the smallest pathway because seems like there are other nodes that have a lower final cost than the school node. So we have to keep repeating this until we find a pathway that gives us the lowest possible value for the path to school. So keep in mind, school isn't final yet because we still are yet to find a path that has a heuristic less than that of the school, right? Now keep in mind, the choice is therefore between F and B. Which one do we pick? Between F and B, please pick the one with the lower heuristic. The one with the lower heuristic, because we're going to repeat this on the one that's closer to the school. So we repeat this on F now, because there's no point in going to B, because B, even though has an overall equal final cost, it has a higher heuristic. So there's no point in going further away from the school node. So what we do is we go to F and we repeat this. Consider that F's cost 8 is final. We tick this off because that's done. And what we do next is we do 8 plus the path cost to school, that is 3. Now is 8 plus 3, 8, 9, 10, 11. Sorry, 8, 9, 10, 11, my bad. 8 plus 3, 11. Is it less than the cost we've got for school right now? Yes, 11 is less than 12. So finally, we've gotten a new value for school. That's 11 as the total path cost with a heuristic of 0, with a final cost of 11. So now we have something very interesting. We fully discovered F, so I can tick this off as well. Right, we fully discovered F. And home was also fully discovered, by the way, right? Home was also fully discovered. I'm putting boxes around all the nodes that are fully discovered. And let me also put a tick next to all the nodes that are fully discovered. And, school has also been traverse to. But the idea is, have we found the shortest path to school? Let's confirm. Now, it seems like if you look at the final cost of school, the final cost of school is 11, but there's still another guy, B, that has a final cost of 11. Now, if the final cost of B is 11, and we are not at school yet, it's almost certain, or it's just absolutely certain, right? That from B to school would be definitely larger, right? Meaning, if you're already at the school and it has a final cost of 11, but you're at 11 and the final cost is 11, right? If you're, sorry, I think I mixed that up, but let me repeat that. If you're at the school and the final cost is 11, and if you're at B and the final cost is 11, keep in mind, B is not the school. B is not where you want to be. But B is not the school, but it still has a final cost the same as the school. What does that indicate? If you want to go from B to the school, then, right, B to the school, then, it will definitely take up more than 11 units of final cost because you're still not at the school, but you've taken up as much distance as the school already, right? So as a result, if by any chance two F values are the same, but if you're already at the school, if you're already at the destination, it doesn't matter whether the other one is equal. What matters is whether this is less than or equal, which it is. So as a result, we can say that we've now come to school and this is final. This, therefore, ladies and gentlemen, completes A star with a path of home to A to E to F, and F to school, right? That'll be home to A to E to F, and F to school. And you can find out that the total path cost to the school is therefore 11, making this A star algorithm complete. All right, guys. So that's the end. Feel free to read through the algorithm again to if you guys want to take a look at any of the specifics. But that's that. In the next part of the video, we'll continue looking at artificial neural networks, deep learning, machine learning, and reinforcement learning, as well as supervised and unsupervised learning. Good luck for your exams.